Hi guys, we're going to start our Faraday's Law of Induction discussion right now. After Hans Christian Ørsted in 1820 accidentally discovered that he could produce magnetism from electricity, Michael Faraday started trying to figure out how to produce electricity from magnetism. So Faraday began his work in 1821 and it took him 10 years to figure out how to do it. This diagram here explains how he did it. So he used an iron ring, and then he wrapped coils around the outside. Remember, we talked about in a previous lesson that having that iron ring in there actually increases the magnetic field strength of a solenoid because it's a ferromagnetic substance. So the first wire, he had a battery attached and a switch attached, and then that wire was coiled around one side of the iron ring. Then he had a second wire that was attached to a galvanometer. A galvanometer is just a really precise ammeter so that you can measure the current that's being pumped through the wire. And that was coiled around the other side of the iron ring. He noticed that when the switch was open, no current was read on the galvanometer, but when the switch closed, he would get a brief moment of current reading on the galvanometer, and then it would go back to zero. And when he opened the switch, he would get another brief moment of current being read on the galvanometer. So it was only in the instance that the switch was opening and closing that he would get any kind of current readings at all. But if the switch stayed open or the switch stayed closed, then there was zero current or 0 amps being read on the galvanometer. So after he made these observations, he came up with his law of induction, which is this equation here in the center of the screen. It says that the EMF, the induced electromagnetic field, remember that's just our fancy way of saying voltage, is equal to capital N, the number of loops in a coil, so how many times he wrapped the wire around the iron ring, times the change in magnetic flux. That's going to be phi b. Okay, so this is the Greek letter phi, and then we're putting a subscript b here because magnetic flux is the perpendicular magnetic field strength over a given area. So these are the magnetic field lines, and then this green square here is the area that those magnetic field lines would be passing through if that square was the iron ring. So let's say this is the iron ring here. We're just going to make it into a square for the purposes of this picture, and then we're just tilting it downward, okay? But these blue lines would still be able to pass through the square just like they can pass through the loop. So I have this iron ring here, and these are my magnetic field lines, okay? So my magnetic field lines can be behind the iron ring in this plane, they can be in front of it, but right here, they can't pass through it because they're hitting the iron ring, okay? So no magnetic field lines could pass through this iron ring because the area, the flat surface of the iron ring itself, is at a 0-degree angle to these magnetic field lines. Now, if I rotate the iron ring so that the magnetic field lines can pass through it, then we would get magnetic flux. Okay, so magnetic flux is measuring how many field lines basically can go through that iron ring's area, and at what angle to the normal would those field lines be passing. And then delta T, of course, is the change in time. How long does it take to do that? Phi, the magnetic flux, is going to be the magnetic field strength times the area times the cosine of theta, the angle between those two vectors, okay? Now we want it to be a dot product, so that's why we have this cosine theta here. If you look in textbooks and things like that, typically it's going to say phi is equal to b times a, but b will have a vector symbol over it, and so will a, or b will have this perpendicular symbol as a subscript, and that's saying that they're both vectors, which means they're cross products. So magnetic flux, phi, is a scalar, which means it needs to be multiplied by cosine of theta to turn it into a dot product instead of a cross product, so it's not a vector sum anymore. So if we look at our one piece of our equation here, the magnetic flux divided by the change in time, this is the rate at which the flux changes, okay? And the rate at which the flux changes is going to be directly proportional to the induced EMF. That's because N, the number of loops around the iron core, is going to stay the same. It's going to stay constant throughout the entire process, so we can ignore that. So that means that this term of the equation is directly proportional to this term. Also, I just said that magnetic flux, if I expand that equation out, it's BA cosine theta. So that means that all of this over here, this is proportional to the EMF that's induced as well. And if we consider this to be a constant, if this doesn't change, and we are only going to change the number of coils, if we wanted to add more or take some away, that would be directly proportional to the EMF or the voltage that we could generate. That means that if you increase the number of coils that wrap around the iron core, then you can actually increase the voltage by just changing the number of coils. So one thing that I haven't mentioned yet is, what about the negative sign? If we look back here, there's a negative sign in front of that N term, the number of loops in the coil. So why is that there? That negative sign is there to indicate that magnetic flux is trying to remain constant the entire time, okay? So anything that you do to the system that would cause a change in the magnetic flux, the system is going to act to try and undo that change so that the magnetic flux will remain constant the entire time. So that means that the electromagnetic force, the voltage, is going to create some current I and some magnetic field B that are going to oppose changing the magnetic flux, phi B, okay? And this is called Lenz's law. All right. Here's where I've written out the magnetic flux equation again. I'm showing you here it's a cross product, and here we're turning it into a dot product so that it's a scalar quantity. And I'm just going through and telling you what each of these variables represents. Magnetic field strength, which is in Tesla. A, the area, which is, of course, meters squared. And then, of course, the cosine of some angle that has no units. That means that the unit for magnetic flux is going to be Tesla times meters squared, which gets its own unit called Webers. And Webers are abbreviated WB. So let's take a look at this practice question over here and see if we can answer it. So we have this iron ring here, and we have a magnetic field that's being indicated with these X's. Remember, X's are like you're looking at the back of an arrow as it's flying away from you, the feathers on the back of the arrow. That means that the magnetic field lines are going into the page, all right? They're going into the screen right now. And our job is to figure out what the value of the magnetic flux would be, phi B. So if we look here, we can see that the angle theta is going to be 0 degrees. So if we look here, we can determine that theta is going to be 0 degrees to the normal. So again, here's the iron ring, and these can be our magnetic field lines, okay? So from your perspective, the magnetic field lines would be pointing in this direction through the iron ring, okay? Now, the normal line, okay, the normal line is normal to this surface of the iron ring, okay? So remember, normal means 90 degrees, right? So the normal line to this flat surface of the iron ring here would look like this, all right? Now, if I point this back up and I put my magnetic field lines through the iron ring, you can see that the magnetic field lines would be 0 degrees to the normal line, okay? The normal line and the magnetic field line would be one right on top of the other. So there's 0 degree angle between the magnetic field lines and the normal line to this area. So this is 0 degrees for theta. and the cosine of 0 degrees is just 1. So we're like multiplying by 1 here. So this term can go away. That means that phi b, the magnetic flux, is just going to be B times A. So they've given me the magnetic field strength is B, and we know that this iron ring here has some cross-sectional area of A, and so that means that phi is just going to be B times A. Okay, let's try another one. So in this picture, we've got magnetic field lines that are pointing straight at the side of our iron ring. So if I turn this, they're right in line with the iron ring. None of them are able to pass through the iron ring, okay? So remember that in this orientation, let me get this adjusted. So in this orientation right here, this is the normal line, okay? So this black pin would be the normal line to the cross-sectional area of the iron ring, okay? That means that it's going to be 90 degrees away from the normal line to the magnetic field line. So we've got 90 degrees between those two quantities, the normal line and the magnetic field lines, okay? So we've got an angle of 90 degrees to the normal, and now we're trying to figure out what phi b, the magnetic flux, is going to be. So remember that we have our equation that says that the magnetic flux phi b is going to be equal to B, the magnetic field strength, times A times the cosine of theta. Okay, so if we have an angle of 90 degrees, then the x and y coordinates would be 0 and 1. And remember, cosine goes with x. So that means the cosine of 90, this is going to be 0. And anything times 0 is 0. Therefore, the magnetic flux in this situation needs to be 0 Webers. So hopefully that makes sense to you. Okay, let's do another one. All right, so in this situation, we have our magnetic field lines are passing through into the screen. So from your perspective, here's the magnetic field lines, and they're going through the iron ring in this orientation, okay? And the magnetic field strength is going to be 0.02 Tesla. And then we have the radius here, r is equal to 0.1 meters. And we're trying to figure out what the magnetic flux is going to be. So I'm going to give you a couple of seconds to see if you can figure this one out on your own, and then we'll work it out together in just a second. Okay, so hopefully the first thing that you did was try to figure out what theta is going to be, all right? So theta, of course, is the angle between the normal line and the magnetic field lines, right? So the angle between the cross-sectional area and the magnetic field lines. So in this case, since the magnetic field lines are going through the iron ring, they are right in line with the normal line. That means that theta is going to be 0 degrees in this case, okay? So theta is equal to 0 degrees. And we know the equation for magnetic flux, phi b, is equal to the magnetic field strength times the cross-sectional area times the cosine of theta. Now, in this case, since theta is 0 degrees, the cosine of 0 degrees is going to be 1 because the x value is 1 at 0 degrees. So that's just like multiplying by the number 1, so we'll ignore that. Okay, the next thing that we need to do is plug in our B, our magnetic field strength. So we have that as 0.02 Teslas. And then the next thing we need to do is plug in our cross-sectional area. The cross-sectional area, since this is a circle, we know that the formula for the area of a circle is pi r squared. And so we've got pi times r squared. So that's what we're going to put in here. We've got pi times the radius was 0.1 meters. And then we need to square that quantity. And then we can plug that into our calculator. Now, sig figs, they only gave us one sig fig up here for our magnetic field strength, and they only gave us one sig fig in here for our radius. That means that we only need to have one sig fig for our magnetic flux. So hopefully you came up with 6 times 10 to the negative 4th Webers. All right, that covers calculating the magnetic flux, understanding what magnetic flux is, what's Lenz's law, and what's Faraday's law of induction, at least at a component level. We haven't actually made any calculations for induction yet, but we will. So please stick with me. In the next one, we're going to figure out how to determine what the direction of the flux is, be able to determine if magnetic flux is changing or not in a given situation. And if it is, then how much current is being induced in the wires because of it. Thanks for joining me today, and I will see you next time. Bye.